An AI model is similar to a boat in that it needs constant maintenance to perform. The reality is, AI models need adjustments, boundaries, guidelines to remain efficient. And when you live in a world where everyone is trying to get bigger and faster and have a certain edge, Scott Clark is helping make that possible with his finely tuned AI modeling techniques.
As you're building up these rules and constructs for how that system will even learn itself, there's a lot of parameters that you need to set and tune. There's all these kind of magical numbers that go into these systems. If you don't have a system of record for this, if you're just throwing things against the wall and seeing what sticks and then only checking in the best one, you don't have a system of what you tried, what the trade-offs were, which parameters were the most important, kind of how it traded off different metrics. It can seem like a very opaque process. So at least that hyperparameter optimization and neural architecture search and tuning part of the process can be a little bit more explainable, a little bit more repeatable, and a little bit more optimal.
More explainable and more optimal, but most importantly, scalable and reproducible. On this episode of IT Visionaries, Scott, the CEO and co-founder of SigOpt, a company that's on a mission to empower modeling systems to reach their fullest potential, explains the basic steps that go into successful models, how his team tweaks and optimizes those models to build more efficient processes. Plus, Scott touches on the future of algorithmic models, including how they will improve and where they struggle. Enjoy this episode.
IT Visionaries is created by the team at mission.org and brought to you by Salesforce Platform, the #1 cloud platform for digital transformation of every experience. Innovate fast, empower every employee, and scale with confidence from anywhere, with a customer at the center of everything you do. Learn more at salesforce.com/platform.
Welcome everyone to another episode of IT Visionaries, and today we have the CEO and co-founder of SigOpt, which is now an Intel company, Scott Clark. Scott, welcome to the show.
Thanks, Albert. Really happy to be here.
Right out the gate, tell us what is SigOpt?
Yeah, would be happy to. So basically, the premise behind SigOpt is recognizing that modeling is an inherently scientific endeavor. Slightly different than traditional software engineering. It's much more experimentation-based, like other scientific endeavors, whether that's hypothesis testing, trying to see whether or not a specific model will even work, or more tuning and optimization-focused experimentation, taking something you have and making sure it performs as well as it possibly can in a variety of different metrics. So SigOpt is a tool that helps developers with this experimentation process, providing a best-in-class optimization algorithm, allowing them to get the most out of their models, as well as a full experiment management suite, providing a system of record for collaboration and reproducibility of this experimentation that would otherwise be lost in a machine learning engineer or data scientist's head, or in a kind of cobbled together set of open source tools.
I remember the first time I talked to someone who told me they were trying to teach or model their TensorFlow machine learning algorithm to catalog scientific research papers. And I remember asking, what do you mean you're trying to teach it? I thought that's the whole point of AI ML, is that it knows what it is. Talk to us a little bit about why does this need to be modeled to begin with? Because I thought you just pump in data and then out comes like an answer, but it's not. But I found out that's not the case at all.
Yeah, definitely. So machine learning is great because it can take data and learn, but the machine learning algorithm itself, as you hinted at, needs to be taught how to learn. This creeps up all over the place. It's called many different things, whether it's hyperparameter optimization, neural architecture search, feature transformation tuning. Basically, it's all the different knobs and levers that you need to set ahead of time before even that first piece of data is put in, so that the machine learning algorithm knows even how to go about doing its learning. In some systems, it's relatively simple. You might have heard of things like random forests or gradient boosted machines, where you need to set the number of trees in that forest. It can also be incredibly complex, where in a big sophisticated deep learning or reinforcement learning algorithm, there might be various stochastic gradient descent parameters, learning rates, architectures, et cetera, that need to be set before the machine can even start its learning. Typically, this is done by the expert by hand or via kind of very arduous, time-consuming, expensive trial and error.
All right, so you just kind of hinted at it, which was that during this process, they described that they would read an article and identify it as, let's say, a scientific peer review or meta-analysis or whatever they wanted to identify it as. And the only way to do it was to have extremely smart people who even knew and can recognize what these scientific research papers were. And then they would go tell the model, like, hey, this is what this is. And I guess it would capture data, language, capture the keywords that it could figure out that says, okay, when I see this, it's a meta-analysis. And it was very manual at first. Because it sounds like SigOpt is a way to make that less manual. I don't want to put words in your mouth, but I'd love to hear how your process differentiates from what I just described, which is I'm going to feed it into a model. I'm going to manually tag it. It's going to give me back a result. If I tag enough things manually, then I'll get back a better result. It makes something in there easier. Talk to me about what it makes easier in that process.
Yeah, great question. So that very manual part of modeling is the labeling process that you described. So needing to be able to get like accurate ground truth so that the model can then use that to generalize and be able to make predictions about things where you don't necessarily have the ground truth already kind of expertly human labeled. And there's really two sides to the coin on how you can make models better. One is giving it better, more accurate data, which is what that's more focused on. And the other is making the model itself more efficient, more accurate, or more intelligent in the way that it uses that data. So in your example, it was more about how do we get it better data, smarter data, faster. Ours is more about once you already have a data set and a model, how do you select which model to try, which variant of that model, which individual knobs and levers of that model to make sure, given your already very expensively acquired data, you're getting the very best version of a more generalizable model out the other side.
How do you, as a builder of a platform like that, determine how it returns a better model for me to choose from?
Yeah, great question. So underneath the hood, we have a variety of different optimization algorithms from like kind of the Bayesian and global optimization academic literature. The idea here is if you have a time-consuming and expensive system that has a variety of inputs and a variety of outputs that you want to maximize or minimize, how do you set those inputs in order to maximize or minimize those outputs? So again, think of it maybe along the lines of you might have a car. The car has a lot of different knobs and levers inside the engine, different gear ratios, different various things that you can tune and tweak. You might want to get the highest fuel efficiency or the highest top speed or something like that. And you would go about tuning that car in various ways. But you as the driver of the car might not have the expertise to do that kind of via intuition. And so you would need a system in order to not just kind of via trial and error, randomly try things, et cetera. Every machine learning system is the same way. Every machine learning system has hyperparameters or potentially architecture parameters or ways that you can transform the way that you're even representing the data itself. And all of those magic numbers govern what the end system will end up looking like. So we bolt on top of these pipelines and allow people to do that experimentation, that exploration, orders of magnitude more efficiently than traditional brute force techniques, and in a much more streamlined and seamless way than kind of trying to cobble it together yourself.
So let's talk a little bit about how you even came about this process as a way of potentially making a product into a company, right? Did you kind of, it's one of the things we always want to learn about people who start companies like this is, did you solve a problem first and found out, oh, I can turn this into a business? Or did you start a business and say, I'm going to solve this problem?
Yeah, great question. So I ran into this problem over and over and over again while getting my PhD in applied math at Cornell. And basically, every single problem that I would make, whether it was in bioinformatics research, whether it was in computational fluid dynamics, whether it was in just kind of more traditional machine learning and AI, would always have this step where we build something cool, we'd apply a lot of domain research, and then ultimately it was up to the grad student in the group to kind of fine tune and tweak it to make it as good as possible before we sent it away for publication. We jokingly call this in our department kind of grad student descent, insofar as it was a very kind of manual process where you had to kind of tune and tweak 5, 10, 20 dimensional systems every single time, maybe hitting a government supercomputer to get results back. But it was inefficient. It was ad hoc. There was no way for like reproducibility, or there was no real system of record besides your log files. And one thing that I found was this wasn't just a problem I was having, but literally everybody in the department was having the same thing, whether they're working in social network analysis, financial systems, whatever it may be. So I was like, there's got to be a better way. Brute force is just, it's mathematically unsatisfying. Doing things randomly, like you don't try to climb a mountain by jumping into an airplane and putting a blindfold on and then jumping out with a parachute and just hoping you land at the peak. You try to build a map, you try to do it intelligently. And so turns out there's a whole class of academic algorithms out there, and Bayesian optimization, black box optimization. Basically, the idea is, how do we efficiently sample complex systems so that we're learning as much as we can, and that's exploration, and then exploiting what we have learned to drive to better and better results, and trading off that exploration and exploitation to ultimately get to the best configurations as efficiently as possible. So I ended up reorienting my PhD and finding an advisor that was focused in this field, used this in a lot of my thesis, ended up writing some open source while I was at Yelp called the metric optimization engine, which was one of the kind of first open source Bayesian optimization packages. This was like 7-8 years ago now. Now there's like thousands of them. But what I found at Yelp was like, not only do grad students have this problem trying to publish papers, but like everybody in industry has this problem too, whether they're building a recommendation system, an advertising system, a classification system, a natural language processing system, like you talked about before. It's a very pervasive problem. It's a very expensive problem. And so it seemed like a problem to build a product and a business around. And that's what we did starting in 2014.
Yeah. So you guys, it sounded like, to answer my question based on what your story said, it sounded like you identified the problem and said, okay, let's build a company to solve this problem. When you first joined, it looks like you were part of Y Combinator. So someone knew what you were talking about. Did your peers know what you were talking about when you were in Y Combinator? They were like, man, this guy Scott, he's trying to say he's going to create a model for ML. I thought ML was the model. Like,
yeah, AI for AI.
AI for AI, yeah.
So to be completely honest, back then there was a small set of people who recognized that this was a problem.
Yeah.
We were going to academic conferences like ICML or NeurIPS, and we could convince experts that this was a problem and that there was a better way. Over the last 6-7 years, though, this has become an incredibly pervasive problem. I talked about us having like the first Bayesian optimization open source packages. Now there's hundreds, if not thousands of them. Other companies have sprung up in our wake. People are realizing that doing experimentation is important, doing it as efficiently is important, and the more expensive the models are and the more computationally intensive they are, the more important it becomes. Early days, we were maybe a little bit early to market, but it's definitely proven itself out as a large market and a very valuable one as well, too.
Yeah, that's one of the things that I always think about when it comes to building forward-thinking technology. I've never hit it. I've made some apps in the past. They never. I'm not rich. But one of the things I always think about, and you can read about, or people can read about, is how a lot of people have great ideas, but a lot of times the timing's not right. Now, you mentioned before when you first got started, people didn't really quite understand what the problem was or what you were solving. Of course, now that has changed, where it's like quite clear that, hey, your software product is going to deliver something. When you first tried to sell it, because that's always a great story for most founders. Like it was like, well, I wanted to take this to market. I had my first customer meeting. What happened when they first heard what you were trying to accomplish and that you wanted them to pay for it?
Yeah, so I guess there's this maybe kind of Maslow's hierarchy of needs associated with modeling. So yeah. I mean, first, and you hit this at the very beginning, is like you need data before you can do anything.
Yeah.
You need like clean labeled data. You need to have a model and a way to like evaluate a model. And like you need those two things before you can even get a baseline, before you can even see whether or not you can have anything at all. And then above that is, how do I do this more efficiently? How do I make this a more repeatable process? How do I optimize this process? I'd say in 2014, a lot of the firms we were talking to, even in the Fortune 500 Global 2000, were very much in that data gathering phase. Mm-hmm. We're just starting to hire data scientists to try the very first line of model. We ended up finding really good grounds for growing with very sophisticated firms. So big AI kind of first technology firms in Silicon Valley, hedge funds. We service over $1 trillion worth of assets under management in terms of like algorithmic trading hedge funds, which tend to be a few years ahead of the pack.
Wow.
We work with like the US intelligence community, and we give the product away for free to academics as well too. So we have about 100 different universities and national labs around the world, from like the MITs and Stanfords of the world to the national labs and like CERN and things like that. So definitely was an early adopter market at the very beginning. But again, as people have kind of increased their sophistication, now they have larger teams, they can build a model, and now they want to build it better. faster, more repeatable. And that's where we can really come in and have this product that's been around and vetted by the very most advanced firms in the world, help them do that right out of the gate.
Yeah, when we first started doing a little homework on you, there were some examples of how you were helping companies do things that used to take 24 days into 3 days. And so like that's on a consumer side, it's easy for us to understand like that's a huge advantage. Talk to us a little bit about what people are doing with this new ability. If we think of a hedge fund, algorithmic trading, I mean, it makes sense. Like they're able to insert their trades faster than someone else would when they believe a stock is, or the model shows a stock's going to go up in price, down price. It doesn't matter. They're, capitalizing in that transaction. But I'd be curious about some of the non-stock trading examples because you kind of hinted at a lot of them. They're going to be pretty exciting. We've on the consumer side, everyone hears a lot about AI, ML reshaping the way products, our society is going to function, the benefits for all of us. But I'd love to hear some of these examples of what for sure, like SigOpt's being used to do this, and this is what's getting better. Like these concrete examples for our audience to be like, oh man, this is cool.
Yeah. So, I mean, just at the high level, like that speed, if taking something from a 24-day process to a 3-day process allows you to, there's a huge opportunity cost there. So like getting things out faster, doing more things. So trying more different models, trying more complex models. So instead of maybe limiting yourself to something very simple because it's easy to experiment with and tune, allowing yourself to take a more complex approach and really having the confidence that you're getting the most out of it. Sometimes a poorly tuned complex algorithm will underperform a poorly tuned just because the simple algorithm has so little kind of band at which it can fall at. You're kind of always going to get a B- answer. Complex algorithm can give you a terrible answer or a great answer. And so allowing yourself the ability to like compare the best versus the best is huge. In terms of concrete examples, we've helped like the world's largest streaming service with a recommendation engine. We've helped like large consulting firms with various projects that they have for their end customers, from like predictive maintenance and IoT pipelines, a lot of algorithmic trading. We help a lot of like credit card firms with the fraud detection. We have a lot of really fun academic examples too. People making like better solar panels or doing kind of predicting diseases more efficiently. And there's several dozen papers that people have published using SigOpt, applying their domain expertise, but using this as a leg up to experiment a little better, faster, get better results, and ultimately push all of their individual fields forward.
When we interview data scientists, people that are in this field, sometimes they talk about how they can't quite explain 100% of all the variables that go into a model, which is might boggle the mind for some people. Like, what do you mean you made it? How can you not know what decision this tool is going to make? Talk about how can it be that someone who's programmed something actually can't quite explain every single variable and how it's weighed in its decision making. To the layman, it's like, how's that possible? You made it. What do you mean you don't know what it's doing? Or I know you have a general idea of what it's doing, but you don't know or do you? Do you know every exact move it's making to say like, okay, this is something or this is something else?
Yeah, great question. So I think it's really the shift from traditional software engineering, which are very kind of deterministic, decision-based processes. If this happens, then do this.
Yeah.
And you can literally explain every reason why you put something in, into these more self-learning systems where you basically give it a construct for how it can create those if statements or make these determinations. But then it goes about building the most efficient set of choices. And sometimes it might be non-intuitive, where you might not have said, well, if this is true, then I'm going to check this other parameter, then I'm going to check this. And you might be able to go back and kind of like reason about why it made that decision, but it might not have been what you did as a human, where you might only be able to think of a handful of variables at a time. These systems can now think of thousands of variables at a time and be able to look through millions of pieces of data. And so they can find little patterns that might not be super intuitive for humans. In addition to that, the problem that we solve more directly is as you're building up these rules and constructs for how that system will even learn itself, there's a lot of parameters that you need to set and tune. And this tends to be this kind of magical black box. There's all these kind of magical numbers that go into these systems. Those themselves have traditionally been very hard to explain because, again, if you don't have a system of record for this, if you're just throwing things against the wall and seeing what sticks and then only kind of checking in the best one. You don't have a system of what you tried, what the trade-offs were, which parameters were the most important, kind of how it traded off different metrics. It can seem like a very opaque process. That's one of the things that SigOpt itself is trying to shine a light on, though, is that experimentation process itself. So at least that hyperparameter optimization and neural architecture search tuning part of the process can be a little bit more explainable, a little bit more repeatable, and a little bit more optimal.
So when you think of the future of what this modeling is going to look like, I was reading this article about someone was talking about how many more of the world's problems are going to be solved algorithmically in the future. You kind of hinted at it, like disease states, disease identification, possible. We've had some people on from Bayer Crop Science talk about how it's going to identify where to grow food. What are some of the things that you think are going to be uncovered in the next 10 years, potentially next 5 years? I get 10 years probably too big of a horizon, like, because someone was trying to explain to me and I had a hard time conceptualizing this. They was talking about the rate of acceleration of scientific discovery of unsolved problems is going to basically go on an exponential curve. And I was trying to think, like, what do you mean like by that? It's like so many, like, if there's X number of problems solved every decade, next decade's gonna be like, X to the fifth power. I don't know, this person was saying, but he was just trying to explain it, like, because you've probably seen your tools being used in arenas that you might not have imagined. I didn't know if you've started noticing that.
Yeah, definitely. And I completely agree that it's exponential. And I mean, you can look at this across technology at any spectrum. Like about 100 years ago is when cars started becoming prevalent. About 50, 60 years ago, like the very first transistors were becoming prevalent. And like now we're having a conversation across the country on a zero latency Zoom call and talking about a podcast about tuning algorithmic trading strategies. So it's definitely accelerating quite a bit. And I think that's only going to continue. Basically, anything that is basically a classification problem. So like, is this one of many potential options? So like yes, no questions are very easy to pipe into these systems. More regression type problems of here's a bunch of data. What's the trend? Like, what can I expect? How can I generalize to unseen data is something that's going to be solved. And then especially with a lot of the new advances in like reinforcement learning, coming up with like policies to solve problems, whether that's self-driving cars or having a robot be able to run into a burning building and save people. I think all of these things are going to become just faster and faster in terms of how they're being deployed.
If software is able to solve so many of the problems, analyze so many problems, it's obviously going to be game changing. I'll use the Bayer Crop Science person just so that you can hear where she was coming from. She was talking about how like certain seeds yield better, like a seed will grow better depending on air temperature, soil temperature, how much water there is, all these things that basically a general farmer can't really measure. But they were talking about how now that they have sensors in the ground, sensors in the air, that they can algorithmically figure out, should I even water the plant in a localized area? And we're like, what do you mean? It's like, I thought the farmers just every day water their plants. Like, no, they don't need to. And she was explaining how all these data points needed to be true to figure this stuff out. And so you're thinking to yourself, geez, like that human decision has been removed, right? It used to be, like you said, it used to be a human decision. Farmer would just come outside and be like, hey, do I need to water the plant? But if algorithms are going to start, it sounds like solving many, many more problems, which problems do you see them not being good at? I'm curious in that, because I was reading also about how TikTok is exceptionally good at finding like TikTok has an unbelievable ability to keep people in platform. And I was reading about this, how when you first start TikTok, you log in and it looks like just jumbled mess, but they said it's like the best platform to figure out, like, you like this. I was blown away. And he was trying to explain to me like how it algorithmically do that. It just went over my head. The reason why I bring that up is because I used to think that computers will never figure out creative, but it feels like they are. Like, it feels like computers are figuring out what you're interested in on a creative basis, which I was like, I didn't know was possible. Do you see domains where algorithms aren't going to be as effective, or is it going to encroach in every domain?
It's a great question. So I'd say one thing that's true about, machine learning and AI algorithms in general is they need to be pointed in the right direction. They can learn novel ways to solve problems, but they need to have metrics that they care about. So in the TikTok example, it wants to keep you on the app. So it can try a bunch of different things, and it can experiment with different content. They can tune their underlying algorithms, but they have this core metric that they care about. If it does worse, you're not in the app as long. If it does better, you're in the app longer. But a human still needs to make that qualitative decision of like, this is something that we're shooting for and want to increase. The machine isn't going to do that naturally. It needs to be pointed in a specific direction. Similar with the crop yields, like deciding whether or not to water the plant, you're doing that in order to maximize yield of that plant or something like that.
Yeah.
But the algorithm on its own, it can take in all this data, but if it doesn't have a reward, if it doesn't know what it's shooting for, then there's nothing to do. So I'd say in certain domains, there's very obvious rewards or maybe sets of rewards that you want to trade off, maybe speed versus accuracy or something like that. And that's where experimentation becomes very valuable because you can obviously understand and make those trade-offs very optimally. In certain fields, the reward function isn't as obvious. Like, what is good art? Again, for maybe something like music, it's like how long somebody actually listens to it. You can come up with a metric like that. But certain music you might listen to a lot, pop songs might be popular now, but like, how do you distinguish that versus like Beethoven and Mozart, things that people will be listening to hundreds of years from now? It becomes a lot more qualitative and there aren't super clear metrics. So I'd say on the creative side, as things get more qualitative, as it's harder to like define what good is, as opposed to just like time in app or yield of a plant, that's the areas where AI is going to continue to struggle until we have general artificial intelligence.
Listen, I met someone who is at Warner Music, music development, and they were talking about how they're already trying to figure out like, will a young new musician, artist, band, whatever, be popular? And so the key is you have to find them before they're popular. So there's really not a lot of data on them, right? So if you were like to check their Spotify ranking, it's like, well, there's only like 7 people that listen to this person, so who cares? Right? And so they're trying to figure out how this happens. So I was curious, I felt like the creative field, but like, I like that. No, that makes total sense the way you described it, where if you can definitively program a metric that says this is the overarching goal, then anything that can be done like that, the algorithms are gonna figure it out.
It turns out that that's a really tricky problem, though. Like even in something that you might think is obvious, like algorithmic trading, going back to that example, you're like, okay, well, the metric is just make a bunch of money, right?
Yeah.
But it's like, okay, well, you need to make money, but also like minimize your risk. And maybe you only have a finite amount of money to trade with. And maybe you need to work in an adversarial environment where other people are going to copy your moves. You start to like boil in all these other constraints or other metrics and things like that. And it's like, wait, this is actually a really hard problem to say what success even is. But like the machine will only do what you pointed at. And this can obviously run into lots of problems too, where if a self-driving car is only trying to minimize time to get to a specific place, it might try to like take shortcuts that aren't on the road or something like that. You need to build all of this in and make sure that the machines know what they're shooting for. And again, that's even for things that have somewhat obvious rewards. It still takes a lot of creativity and qualitative experimentation in the metrics themselves to make sure it's pointed in the right direction.
That's a great point. I'd love to, your self-driving car sees a road, it's got a road closed sign and starts trying to figure out like, is the road actually closed? If it determined like it's not, it's just a sign. It just goes around it.
Yeah. I mean, it depends on what its reward function is. If it's get to from A to B as fast as possible, then it's like, well, it's slightly faster to cut across this field or something like that.
No, it's fascinating when you talk about autonomous driving. Now, this is one of the things I asked. I've always wondered, and I continue to wonder, when it comes to autonomous driving, the one thing I think people will have a hard time with is they want to know what it's programmed to do, if it's to preserve the driver's life or life in general. Because not that it happens often, but there are times when obviously automobiles are in grave jeopardy. And so I wonder if it algorithmically figures out like, oh, well, your life is worth most, so I will save you versus me saving your life is going to cause problems. Therefore, I will not save your life. Like I don't think anyone wants to buy a car that's not optimized to save their own life.
Yeah, I mean, this is the trolley problem, right? And it's bothered philosophers for many, many generations. But I think, at the end of the day, the trolley problem is a hard problem, but you having the agency to control the problem versus handing over the trolley problem to someone else or something else is what can give people pause.
It looks like you guys started Y Combinator, built the business up. It's now publicly known that Intel has acquired the business. Talk about what that means for you in regards to like pushing this algorithm further. I mean, you mentioned before that getting access to data is the number one thing. Like once you have access to data, your ability to then get the better answer is amplified. So now you're under the Intel umbrella. You got more customers, to work with, more resources. Everything's more. Talk to me about what that's doing for SigOpt and what you guys are up to now.
Yeah, great question. So we're super excited to join the Intel family. I think, as you said, it gives us access to more developers, more customers, more problems. We can join forces with all the great work that's happening within Intel to make those processes more efficient, more optimal, better experimentation, et cetera. Intel has this great ability to really democratize AI and bring AI everywhere. My computer has an Intel chip in it. I'm sure yours does too.
Right.
And really pairing that great hardware with great software and services can really change the way that people attack this problem. So again, back to what I was saying before, where some of our early customers were the most advanced firms in the world, the intelligence community or the algorithmic traders and things like that. I think more and more AI is becoming more pervasive. You could take a class today to start training a model within an hour, but making sure that you have the right hardware, the right software to do that as well as possible, I think is just becoming more and more ubiquitous. And we're super excited to join Intel on that mission to bring AI everywhere, give people the right tools to get the most out of their hardware, to get the most out of their expertise.
So how about for yourself personally? Are you more doing like your daily assignments? Are you doing more development work, or are you leading more data scientists? Like how's your responsibility, I guess, shifted?
Yeah, great question. So, I started SigOpt because I had this problem because I wanted to accelerate and amplify the impact of modelers. As a startup CEO, I did a lot of work in doing B2B enterprise sales, doing fundraising, doing board management and things like that. So one of the great things about joining Intel is it allows us to focus on our mission and really focus on the users and build great things for the users, as opposed to trying to become a multi-billion-dollar profitable company independently. And that focus on the users, focus on that actual experience, I think is good for us because we get to do what we love and have a big impact in the world. But it's also good for all of Intel's customers who get to benefit from that focus as well.
So how many people on your team now is trying to attack this problem?
So we're 24 people today, but looking to grow. So if you're interested in experimentation and joining a great team, we'd love to hear from you. So SigOpt.com.
There you go. Hey, listen, you got to plug yourself, man. What kind of people are you looking for? What kind of domain experience they need? Because you guys are at probably a new level. I don't even know. Do schools even teach what you're trying to have people know? Talk to us about what that's like recruiting.
Yeah, great question. So, we build tools to help experts do their jobs better. So fundamentally, it's about empowering experts. We don't need to have expertise in every field in order for us to build tools to make those experts more efficient. So we're looking for product managers, designers, software engineers that can help take this technology, make it easier to use, more intuitive, and basically allow these experts to stand on shoulders of giants and be able to leverage the best possible tooling. And so you don't need to be an expert in everything. We do have a research team that does have expertise in kind of Bayesian optimization and global optimization. But at the end of the day, it's really about how do we build tools to make people more efficient? And there's a lot of people that can contribute to that.
Well, Scott, it is now time for the lightning round. The lightning round is brought to you by Salesforce Platform, the #1 cloud platform for digital transformation of every experience. Scott, this is where we ask you questions outside of the realm of work so our audience can get to know you better. You ready?
I'm ready.
Okay. Do your parents know what you do?
They try. I like to use analogies a lot, so they'll usually latch onto the analogies.
Sounds good. While you were at Oregon State, it looks like you were a big sports fan. Is that accurate?
Yeah, I huge Oregon State football fan.
Yeah? And you used a climbing analogy. Are you an outdoors person as well?
Yeah, grew up in Oregon in the Pacific Northwest, so a lot of outdoors, a lot of climbing and hiking, and yeah, enjoy all that.
So did anyone else that was in your physics, computational physics, and mathematics classes also enjoy the outdoors with you?
Yeah, Oregon State attracts a very diverse set of students, and being in the Pacific Northwest, being in Corvallis, a little town in the middle of nowhere, the only thing to do was to get outside.
Now, you mentioned before you spent some time in Cornell, and then you had to work a lot in New York, it sounds like. So you got to tell our audience, what's better, the big city of New York or the mountains of the West?
Well, it really depends on your metrics, like we talked about before. So they're both Pareto optimal in different areas.
How about personal enjoyment for you?
I enjoy living in the Pacific Northwest, although I do visit New York frequently and really enjoy that. But 24/7 Manhattan might be a bit much for my personal taste.
Not a problem. I'm with you. I enjoy the outdoors as well. Scott, it was a pleasure having you join us on IT Visionaries. Thanks for sharing what you've done at SigOpt. Thank you for explaining how modeling is actually the key for AI and ML to work. I hope you had a good time, and thanks for sharing your story.
Thanks for having me, Albert. I really appreciate it.